People often think of the ocean as moving only forward and backward, but under certain conditions, water begins to rotate around itself. When this rotation becomes organized and sustained, it forms a whirlpool, a phenomenon that can appear calm at a distance while containing significant force closer to its center. This narration explains what a whirlpool is, how it forms, where some of the strongest examples occur, and how its real behavior differs from common portrayals. The focus is on the physical processes that drive rotating water and the limits of its effects, based on observable mechanics rather than legend. A whirlpool is a rotating mass of water that develops when currents moving at different speeds or directions interact, or when a large volume of water is forced through a confined space. As these currents meet, the water begins to circulate around a central axis, creating a vortex. This process occurs at many scales. The same principles that govern large ocean whirlpools also apply to smaller rotations seen in rivers, near waterfalls, or in household drains. The difference lies in scale, not in underlying physics. The rotation of a whirlpool is driven by momentum and pressure. Once water begins to move in a circular path, it accelerates as it approaches the center of rotation. This acceleration reduces pressure at the core of the vortex, sometimes producing a visible depression on the surface. Gravity maintains the overall movement, while surrounding currents continue to supply energy. The persistence of a whirlpool depends on how long these conditions are sustained, which is why some dissipate quickly while others remain active for extended periods during strong tidal flows. Whirlpools do not function as vertical suction forces pulling material straight downward. Their motion is primarily horizontal and rotational. The associated risk comes from the strength of the circulating current, which can disorient swimmers and make maneuvering difficult for small vessels. Larger ships are rarely affected in a meaningful way because their mass and momentum exceed the force generated by most whirlpools. Some of the most intense whirlpools form in narrow marine passages where large tidal volumes move through restricted channels. In these environments, water speed increases significantly, enhancing rotation. The resulting vortices can be wide, visually distinct, and accompanied by loud, continuous noise created by turbulent flow. Before the mechanics of tides and fluid motion were understood, such conditions were often interpreted through myth, leading to exaggerated accounts of their power. Historical descriptions frequently portrayed whirlpools as deep openings extending into the ocean, but modern observation shows that even the strongest examples are surface-driven systems. They do not form permanent vertical shafts, nor do they connect directly to the seabed. Their danger lies instead in the combination of sustained currents and the physical strain they place on those caught within them. Beyond their immediate effects, whirlpools are of scientific interest because they provide insight into fluid dynamics and energy transfer. Studying rotating water helps explain broader patterns in ocean circulation and contributes to understanding larger rotating systems, including atmospheric storms. The same physical principles that shape whirlpools influence many natural processes where rotation plays a central role. Whirlpools can be observed wherever flowing water encounters imbalance, whether in open seas or confined waterways. Many are minor and pose little risk, while others reflect extreme conditions that require caution. Knowledge of how they form and behave replaces speculation with measurable cause and effect and allows their presence to be assessed realistically. These rotating systems demonstrate how organized motion can emerge from simple forces acting together. Without requiring exaggeration or symbolism, whirlpools show how gravity, pressure, and momentum interact in visible ways. Understanding these interactions provides a clearer view of the natural processes that shape moving water across the planet.